Have you ever sort of imagined a world where you could design something really complex, like, say, a bridge that stands against any stress, or maybe a new medical device, even the structure of a living organism?
Right.
But not by drawing every little detail, which takes forever, but just by telling a system what you want it to do, what properties it should have.
Uh-huh.
And what if you could instantly know, say, the structural integrity of a skyscraper or, I don't know, the
Well,
flow dynamics in a new organ before you even sketch a single line?
Yeah, that's the dream, isn't it? Predictive design.
Exactly. Well, today we're doing a deep dive into an invention that sounds like it comes straight out of that dream. It's born from some really fascinating conversations, a project called Topy,
Topy, yeah.
yeah.
It's essentially framed as a topology OS.
an operating system for shapes. We're going to explore how this Topy idea promises to, well, fundamentally change how we think about design, maybe even mathematical discovery, and perhaps our whole concept of truth.
It's a big claim, but the framework is compelling.
Our mission today is to unpack that journey. How did it go from a technical AI idea to this much broader philosophical framework? We'll look at how Topy uses things called imaginary matrices and speculative decoding
Concepts will definitely break down.
to create basically a recipe book for shapes,
Mm.
making things that seemed unbuildable or at least hard to predict suddenly quite predictable.
Mm.
Okay, so the vision here for Topy is, well, it's huge. Revolutionizing how we design and understand shapes, moving way beyond traditional methods. Let's dig into the core of it.
Okay, so what's really fascinating, I think, is the foundation. It takes this concept, speculative decoding.
Which comes from AI, right?
Yeah.
Language models.
Exactly. Originally used in LLMs to predict text, check the next word, check if it makes sense, and it applies that fundamental idea, that principle, to the actual structure of shapes.
Yeah.
It's leveraging that guess and check idea, but in a really sophisticated way, for geometry and topology.
So if I'm getting this right,
Mhm.
instead of me drawing out some complex object bit by bit,
Right.
I could just sort of describe the topological features I want, how it connects, how many holes.
Precisely. The intent.
And Topy would then, what, instantly predict the best outcome? Like a shape synthesizer?
Well, instantly is the goal, certainly much faster. Imagine Topy generating a possible topological blueprint based on what you asked for. Then it runs a very quick, low-cost check against those properties.
Okay.
If it looks good or close, it refines its guess. It iterates until the approximation holds up. Only then does it maybe move to a more rigorous check. But even that is designed to be super efficient.
So it's discovering algorithms on the fly.
In a sense, yes. It's discovering highly efficient ways to map the shape's geometry to its algebraic fingerprint. You mentioned holes, connectivity, maybe inherent twists. It's like a guess and check, but for the algorithm itself.
Wow.
A fast guess guides a more careful check. And crucially, it learns to get better, more efficient each time.
Okay, I'm trying to picture this. How does this speculative idea work with actual, tangible digital shapes, like the ones made of triangles we use in 3D modeling? What about something tricky, like a Mobius strip?
Yeah, good question. Building on that idea of defining shapes by connections, triangle meshes and their 3D versions, tetrahedral meshes, they are pretty much the universal standard, the building blocks for digital shapes.
Right.
And that weird twist in a Mobius strip, it's not just something you see, it's fundamentally baked into the connectivity of that mesh, how the vertices, edges, and faces link up. That defines its topology.
So Topy wouldn't just look at the surface, it digs deeper.
Exactly. It might have this multi-stage approach. First, maybe a quick broad check,
Oh, yeah.
like calculating the Euler characteristic. It's a simple topological number you get from counting vertices, edges, faces. Gives you a quick feel for the shape's overall form.
Yeah.
But for some shapes, like a cylinder and a Mobius strip, that number is actually the same. It's 0 for both.
Ah, so it's ambiguous then.
Right. So if that first check isn't enough, Topy doesn't give up. It then runs a more targeted but still very fast local test. Specifically, it checks for orientability.
Orientability.
Yeah.
Like whether it has a consistent inside and outside.
Exactly. And for the Mobius strip, that test immediately flags it. Non-orientability detected. A cylinder doesn't have that issue.
So it escalates its analysis only when needed.
Precisely. That's why it's called a self-optimizing topological machine. It's smart about computation. It only ramps up the effort when the simpler checks aren't enough, learning to pinpoint the exact topological feature with minimal work. So Topy gets clever about checking things. But to really design shapes based on intent to create new forms, we need a language that speaks directly to the, let's call it the algebraic soul of shapes, bypassing the geometry itself initially.
Okay.
And this, for you listening, is where this really interesting idea of imaginary matrices comes in. It's about working directly with the shape's algebraic DNA.
Imaginary matrices. Okay, my first thought is the II from complex numbers in math class. Is that it? Sounds pretty abstract.
Yeah, it sounds like that, but no, not quite literally using I. It's imaginary, more in the sense that they exist conceptually as a powerful abstraction layer.
Okay, an abstraction. How does that work?
Imagine a matrix, rows and columns. But instead of numbers in the boxes, each entry is an instruction, an operation you want to perform on the shape's topology.
Like commands.
Exactly. Commands like add handle, think adding a handle to a mug,
Sure.
or add twist, like creating that Mobius property, or maybe extrude solid. These operations are what mathematicians call functors.
Functors. Okay, remind me.
Basically, they're mappings that preserve structure. In this case, they preserve the topological structure even as they transform the shape. So you're combining matrix algebra, which is well understood, with these topological operations.
Creating a new kind of algebra for shapes.
A brand new algebraic structure, yeah. It lets you represent and predict really complex transformations purely abstractly without ever needing to actually draw or render the geometry until the very end.
Wow. So these imaginary matrices, they become like a control layer, an operating system for topology, like you said earlier, predicting outcomes using just algebra without messing with the geometry directly.
That's the core idea, like writing code for shapes rather than drawing them.
That really does sound like an OS for forms. It changes everything.
Yes, precisely. And this system, this Topy, it completely flips the traditional design process. Normally it's build something, analyze it, tweak it, rebuild it, repeat.
Which can take forever, especially for complex stuff.
Weeks, months sometimes. Topy aims for specify your intent algebraically, predict the outcome, then generate the geometry.
Algebra first.
Algebra first. The potential for efficiency gains is just monumental. These imaginary matrices essentially compress enormous geometric complexity into these concise algebraic recipes. It provides a single, unified way to think about manipulating shapes, no matter if it's 2D, 3D, or something more complex.
Okay, let's ground this a bit. What does this mean for, real-world applications? The inventor apparently threw out some incredibly ambitious ideas, like creating a formula for the human body, or the math behind Star Trek's tricorder.
Yeah.
That's aiming high.
It is ambitious, definitely. But what's exciting is just how broad the potential applications seem. Imagine, for instance, a topological atlas of human morphology.
Okay.
So every part of the body, a bone, an organ, maybe even a facial feature, wouldn't be stored as this massive, heavy 3D scan file.
Right, those can be huge.
Instead, it would be represented by a lightweight Topy pattern. This pattern is basically an algebraic summary. It captures the essential topological relationships, how it connects, how it bends, its fundamental harmonic properties, the underlying shape DNA, if you will.
So you could then have algebraic operators that represent biological processes, like you mentioned I at volume or I apply aging durations.
Exactly. And Topy could predict the outcome of, say, cosmetic surgery or reconstructive dentistry or designing incredibly personalized prosthetics all algebraically before anyone makes a single cut or prints a single part.
That would be absolutely revolutionary for medicine and bioengineering, moving from reactive fixes to truly predictive design.
That's the vision. Testing thousands of variations in seconds, predicting function and aesthetics with incredible accuracy. Or think about that tricorder idea from Star Trek.
Yeah.
Topy could be the mathematical engine inside a device like that. You scan an object, it processes the algebraic signature.
It's Topy pattern.
Right. And it instantly tells you its properties or how best to modify it. It's about non-invasive, immediate understanding of form, making abstract topology tangible and useful.
So it could be a language for the human form itself.
That's the hope. The inventor did often joke, that Topy was his way of trying to make a bit of Star Trek real, starting with that tricorder. And, it goes even deeper than just designing things faster or understanding bodies better. Topy starts to push at the edges of how we think about mathematical truth itself. Discovery. Proof.
Okay, yeah, this is where my mind started bending earlier. The inventor questioning if Topy could somehow transcend really big abstract math problems, like the Hodge conjecture. and bringing in names like Marx and Hegel. What's going on there? How does a design tool connect to philosophy and fundamental math?
It's a fascinating leap. It asks this question: can a system achieve truth by synthesis? Let's take the Hodge conjecture. It's a famous, very difficult, unsolved problem in math. Super simplified, it asks if certain complex geometric features are always linked to simpler algebraic descriptions.
Okay, a deep connection between geometry and algebra.
Right. Now, Topy doesn't try to prove that conjecture in the traditional, formal, step-by-step deductive way. Instead, it operationalizes it. It builds the principle into the system. It basically says, look, instead of spending decades trying to formally prove this connection exists, let's build the system where this connection is assumed to be true. Like, it's the physics of how the system works.
So you tell Topy, I need this kind of bendiness, which is geometric.
And it uses those underlying algebraic relationships, the ones the Hodge conjecture talks about, to generate a successful functional design, a beam, maybe.
And the fact that the beam works, that it holds up,
implicitly validates the principle it was built on. It demonstrates truth by synthesis, truth through successful doing, through construction, not just through abstract proof.
So Topy becomes a sort of concrete antithesis to these purely abstract formal problems. Its success in the real world, its ability to reliably turn intent into reality, makes the truth of that conjecture a practical working reality, even if no one's written down the formal proof yet. Is that like a materialist dialectic of shape, where the doing validates the theory?
That's a great way to put it. You've nailed it. And yeah, this perspective connects surprisingly well to the 19th century philosopher Joseph Dietzgen.
Dietzgen, okay, not a household name for most.
No, but he had this materialist idea that thinking itself is a material process tied to our interaction with the world, and that truth isn't just abstract logic. It comes from practical utility, from successful construction, from making things that work.
And Topy is like externalizing that process, putting the brain work into the machine.
In a sense, yes. It demonstrates that the functional success of a system can be its own powerful form of validation. It helps us get beyond just relying on empirical checks or getting stuck in loops of abstract logic. The inventor saw it as bringing Dietzgen's 150-year-old philosophical insight into the 21st century, using computation.
Okay, so this is much bigger than just a piece of software. It's aiming to establish a new operational philosophy in mathematics. Maybe even, like you said, reviving Dietzgen for the modern age. If that's the goal, what are the concrete next steps? How do you move this from idea to undeniable demonstration?
Well, the most strategic path forward seems to be twofold. First, a really rigorous mathematical paper laying out the theoretical framework clearly.
Okay, academic grounding.
Exactly. But theory isn't enough here. It needs to be paired with a strong computational validation project, something we've been calling a Hercules project.
Hercules project. Why Hercules?
Because the idea is to rigorously test Topy on a really challenging, complex topological optimization problem, something that would be, well, a Herculean task for traditional methods, like designing a Hercules beam, a structural beam with incredibly intricate internal geometries optimized for strength, weight, maybe material use, or perhaps a complex mechanical part needing very specific fluid flow properties.
Gotcha. So the plan is implement Topy, maybe in Python or a similar language,
Right.
and show that using these high-level commands, this intense specification, it can efficiently find optimal designs for something genuinely difficult. Designs that might outperform or at least radically speed up traditional methods that rely on endless simulation and manual tweaking.
Precisely. That becomes the undeniable proof, the pragmatic transcendence. It shows that this dialectical approach theory, grounded in practice, validated by computational success, is a powerful way forward. It's how you demonstrate you found a way out of the slower, more iterative cycles of conventional design and discovery. You specify the topology, let the algebraic engine run, and get validated, often elegant designs, much faster.
It's building knowledge through construction.
Exactly. Proving the philosophy works by showing what it can build.
So let's recap. We've journeyed through Topy, this really revolutionary concept of a topology OS. It's about shifting design away from trial and error towards something predictive, driven by intent, using these core ideas of imaginary matrices and speculative decoding.
Turning design into a conversation with algebra.
Right, and we saw it's not just a tool, it's almost a philosophical instrument. It embodies this idea of truth by synthesis, connecting back to thinkers like Joseph Dietzgen and potentially pioneering a whole new operational philosophy for math. It's quite a trip, from AI techniques to rethinking truth itself.
Yeah, Topy fundamentally isn't just for engineers. It's framed as maybe a new kind of telescope for mathematical discovery, a sort of universal translator between our geometric intentions and the underlying algebraic reality. It suggests the universe might have this innate language of form.
And Topy is the first compiler for it.
That's the provocative idea, allowing us to not just observe, but actively sculpt reality using this language.
Which leaves us with a pretty profound final thought. If a system like Toki can actually embody and validate deep mathematical truths just by working, by operating successfully making abstract ideas concrete and functional, what does that really mean for how we think about proof and discovery? Could Topi help us uncover fundamental laws of the universe we haven't even imagined yet, by allowing us to actively program forms and functions, not just observe them?
A powerful question to ponder.
Definitely something to think about. We encourage you, our listeners, to mull over these ideas, maybe explore computational topology a bit, or perhaps even look into the rather intriguing philosophy of Joseph Dietzgen.